of viewing stone appreciation. This ancient art form began in China and spread to Korea and Japan, and then much later spread to the Western countries. Let's see. Do you have the first slide up on your show? Oh, there we go. Now we're back. Now we're cooking.
Yep.
Okay. Now, today's program is the science of patina and its application to viewing stone appreciation. It's brought to you by VSANA, the Viewing Stone Association of North America. Our goal is to provide accurate information about certain stones that have the ability to invoke feelings and something greater than just a rock. At this point, I'd like to ask you to mute your microphones. If you have questions during the program, please use the chat box, and we'll be sure and watch for those and answer them. Then at the end of the program, we will open it up to all of the viewers so you can ask questions. And we enter into a discussion with Steve and Sue and myself, and we'll learn from each other. Your cooperation on this will result in a much smoother, uninterrupted program. I'm delighted to welcome two guests today, Dr. Steve Tait and Dr. Susan Tait, both professionals and who have been involved in the study of corrosion and surface issues with minerals, gems, and building materials through their career. And they have a consulting company and have advised major businesses, cities, industry about issues relating to surface changes on metals and stones. And so I can't think of a better qualified duo to address the subject of patina than Dr. Sue Tait and Dr. Steve Tait. Now, the subject of patina on stones is particularly important in viewing stone appreciation practices. A stone should not appear to be freshly harvested or carved. Instead, it should have an aged appearance, suggesting an elegance, a feeling of elegance and steeped in history. The expression of oldness comes largely from the surface appearance of the stone, its patina. Now, the aesthetic quality of old or oldness originated in Chinese Shangxi practices. And Bob Mowry, a well-known sinologist, wrote about this in his book, World Within Worlds. And the feature of oldness dates back to the Ming and Qing dynasty from 150 to up to 500 years ago. Now, the use of the appearance of oldness was adopted in Japanese suiseki evaluation practices and is still used today. Now, what is patina? Today, we will take a look at the subject from the view of two scientists who are experts in geology and the subject of corrosion on stones and metals. Now, why should we bother with this? Well, if you want to become a viewing stone connoisseur, you need to be well-versed in all aspects of viewing stone appreciation. And this is a particularly important one. At this point, I will turn the program over to Steve, who will pick up on this at this point. So Steve, it's yours.
Thank you, Tom. And welcome to everybody from Sue and myself. Patina is an old term. It's appeared around the 1700s to describe the green coating on copper, bronze, and brass. We have two examples of that here. On the left is a native copper ore with the very dark green copper oxide, hydroxide sulfate, copper sulfate patina. And then of course, to the right is an example of the viewing stone with the old, or the, shall we say, mature look of a patina. In the next slide, we talk about the definition of patina. It's interesting because you hear patina applied to a lot of different things. It would be, yeah, there we go. So when we started this, to assemble the seminar, I asked Tom if he'd run a survey of VSANA members and ask them, what's your definition of patina? And he got a good response. And so at first you look at it, you say, wow, I've got a bunch of different responses. But when you look at it closely, there were several attributes that appeared in all of their definitions. These are shown, the words and phrases in the green. First one being coating, surface, appearance that changes with age. So if we add a few scientific terms to this, we come up with the definition of patina is a stable, thin coating on a viewing stone surface whose appearance, color if you will, changes with age. Now we've got a framework to work with. And by using that framework, we can categorize viewing stones or stone patinas into several different areas. There's metal oxalate patinas, ones that you find on carbonate viewing stones. Varnish patinas, we were talking about that a little earlier. Desert varnish, rock varnish, desert varnish being 4 to 12 inches annual rainfall, rock varnish being more than 12 inches. There's rind patinas, chemical weathering, metamorphosis, and we're actually doing some research on what I'm referring to as a metamorphosis using Lingby and Mount Pellet, well, actually the Ligurian mountain range of stones, and then artisanal patinas. Well, we don't have enough time to talk about all of these today because the topic is enormous. So on the next slide, we show, we're going to pick 3. We're going to talk about the metal oxalate patinas, desert varnish patinas, and artisanal patinas. So on the next slide, we have the outline for the seminar. And we'll first start off with some scientific terminology that's relevant to patinas, talk about the sciences involved in patina research, how viewing stone patinas are formed, and there's the 3 that we'll cover, the metal oxalate, desert varnish, and artisanal, and then finally pull together a summary. So next slide, let's talk about scientific terms relative to patinas. And you say, oh, well, gosh, I'm not interested in science. Why are we bothering with this? Well, I put approximately 12 art and science disciplines. Sue informed me that there's more like 20 art and science disciplines involved in patina research. Each has its own language. For example, the word rust. Well, to me, rust is that, corrosion product on a metal surface that, like the patina on the copper. If I asked Tom and he didn't know me, he's a botanist, and say, what does rust mean to you? He would say, well, that's the fungus that you find on plant leaves. Same word, 2 entirely different definitions. So hence we want to go over some scientific terms. The first 2 are surface science terms. We talk about adsorption, ad meaning what it sounds like. Something's put on the stone surface and it bonds to it. We talk about absorption. In this case, the material becomes part of the stone. It penetrates into and under the stone surface. We have hydrolysis. That's when water breaks the mineral bonds and forms patinas. Hydration, when water adsorbs, sits on the surface of the viewing stone and actually creates another mineral. So in the next slide, yes, we'll talk about oxidation. Now, oxidation is a change of state from a neutral state, like the metal atom, to a oxidized state where it has a +1 or so charge on the metal ion. So on metal atoms going to a metal ion, best example of this is probably that most people have seen is you've got a piece of silver plate or silver. As time goes on, it develops this dark, almost black color. If you wait too long to clean it, it gets even blacker. This is the oxide. Well, it's not an oxide, it's actually a sulfide. But this is your tarnish or your patina. And this is a case where oxygen wasn't involved in the oxidation reaction. Well, in the next slide, we talk about if you got oxidation going on, you have to have reduction. In other words, nature likes to balance things out. So I've taken an example of an acid solution shown in the chemical equation underneath the title reduction, where you got 2 hydrogen ions, that's the acid. They're in a +1 state. They're going to come along and steal some electrons from a metal or whatever they can get it from, and they're going to become neutral. They've been reduced from +1 to 0, hence reduction. Mixotrophic microorganisms.
Oh.
These are bacteria and fungi that produce their metabolic energy by oxidizing metals. They're often involved in forming patinas. In the next slide, we talk about different scientific disciplines that are involved. We're going to go through 4 of them. I didn't list biology here because we're going to talk about that in detail. Surface science, mineralogy, climatology, and atmospheric sciences as it relates to contaminants. So let's start off with surface science in the next slide. If you could see the atoms in your viewing stones, it would look like this ball and stick figure where the green little balls would be your mineral atoms. I've highlighted the upper right-hand corner with the dashed red lines to show that it's a cube and that the entire structure is composed of a bunch of tiny little cubes stacked together side by side on top of each other and so on. The interesting thing is that what you would see in the mineral, like the pyrite to the right, has the same shape as the little cube does. So nature, you actually can see the structure, the molecular structure, what it is, just looking at the mineral sample in a lot of instances. In the next slide, we're going to focus on the surface of this diagram. I've shaded it just kind of a pale lavender color. Surface, most of the time, is the first couple of atoms. It's very, very thin. Lots of zeros in front of a number. Below the surface is a subsurface. Below that is your base stone. Let's focus on the surface. This is where you touch your viewing stone. When you pick it up, this is where you make contact. This is also where the patina is going to form. If you look at the atoms at the top on the surface, they don't have an atom sticking up or hanging up above them. Because of that, they become unstable. And in the next slide, we talk about all surfaces are thermodynamically unstable. However, this instability is what allows chemical reactions that produce your patinas. Another thing about surface science is water is an essential ingredient for reactions. Where's your water coming from? Rain, dew, humidity, when it's greater than 50%. As a matter of fact, all surfaces are underwater when the humidity is above 50%. And in the next slide, I'm going to show you an example of that. Granted, you're under only about 30 water molecules of water, but nonetheless, you're underwater. This is it's concrete, essentially a man-made stone. This is early springtime in Wisconsin. At that time, we have ice storms, although we've been getting them a lot here recently instead of snow. And we use a snow melt. We spread it on the sidewalk so that we can walk on. If you notice, the two arrows there are pointing, the two white arrows at the bottom are pointing to two white particles. These are particles of the snow melt that are on the surface. If you look closely, and I'll have Tom circle these for you. You can see on the one on the left, you can see the halo surrounding the particle there. And then if you look at the one at the right, you have the same sort of thing. What's happening is these particles are attracting and trapping water. And that's going to be important when we start talking about how patinas are formed. So if I could have the next slide, please. Let's talk about mineralogy, that's stone properties, hardness, density and porosity, solubility in acids and water. These properties are going to interact to determine a number of things about your viewing stone. One is shape, intricacy, and the other is whether or not a patina forms and what kind of patina you're going to get. So in the next slide, we're going to talk about two extremes. We'll start with carbonate stones, limestone, dolomite, malachite, and so on. These are soft stones. They're soluble in most acids. By softness, we're talking about 3 to 4 Mohs. They have low density, 2.5 to 2.7 grams per cubic centimeter, with a corresponding high porosity. With these kinds of stones, water and wind are going to erode the carbonates without abrasives. If you look at the figure on the right, this is a viewing stone photo provided by Tom. You can see the points, you can see undercuts in it, and you can see how rough the surface is. So the acid solubility then allows an oxalate patina to form on this. And in the next slide, we have a hard stone. I'm going to pick on jade and quartz. These are silicate stones. Yes, I know that your phyllosilicates like serpentine and talc are soft. We're talking extremes here, so we're going to talk about the hard ones, and this would be jade, quartz, and so on. These are sparingly soluble in water and most acids. I say sparingly soluble because water's the closest thing to universal solvent, and it will dissolve it, but it's a matter of how much. In this case, very sparingly. Hardness is hard, 7. High density with a low porosity, densities around 3 grams per square centimeter, or cubic centimeter, excuse me. Water and wind typically are needed to abrade these materials. It's not necessary. I mean, if you got 30 million years or so, you can erode them also, but the abrasive make it goes a little faster. If you look to the Alaskan jade sample to the right, this was picked out of a stream in Alaska, and you notice that instead of the sharp features, we have rounded features on this. And I don't know, could we zoom in on this one a little bit, Tom? Perfect. If you look at, it's hard to see, it's at the top, about a third of the way there, there's a real smooth looking black surface there. And that's, that's another feature of the hard stones is you can get a nice, smooth, bright to waxy surface polish. However, it's unlikely that you're going to form an oxalic patina on this kind of material. Well, in the next slide, we talk about some additional science. We recap just showing the difference between the soft and the hard. You can see with the viewing stone on the left, you have a lot of sharp points, a lot of undercuts, rough surface, whereas the hard stone on the right, rounded surfaces, it's smooth. So yeah, the next slide then, we'll cover just some more of the science, talking about the climatology, annual rainfall, temperatures, soil composition. And we'll move on to the next slide where we talk about the atmospheric part. Now we bring in the biology, microorganisms and spores, volatile organic compounds, naturally methane, but automobile exhaust and so on. Inorganic particles from fires. We had a lot of news, a lot of fires in the news last year in the United States. Hopefully we won't have very much, or hopefully none. Volcanoes, industrial pollution, industrial gases, and dust. We hear about a couple of times a year about the desert winds that spread all over the planet, bringing silica with them. So the next slide. Now we're going to talk about, oops, excuse me. So to recap all the science factors, will a patina form? Well, it depends on the interactions between many surface science, mineralogy, climatology, and atmospheric factors. A lot of scientific research going on, but certainly more is needed to completely understand these interactions. And in the next slide, we're going to start to talk about now how patinas form. We're going to cover 3: metal oxalates, desert varnish patinas, and artisanal patinas. I can't stress enough that these 3 are chemically very, very different. They're morphologically very different. Morphology being the structure and the texture and so on. And they are formed in very different ways. So let's start with metal oxalate patinas. If I can have the next slide, please. This is an example of we'll talk about metal oxalate patinas where the annual rainfall is greater than 12 inches. This is a piece of Wisconsin limestone. If you drive through road cuts, which you have a tendency to do when you're traveling in Wisconsin, this is kind of what the limestone would look like. If you go through deep cuts, you'll find a very high, very deep layers of limestone, and then underneath the dolomite, which is a magnesium carbonate. I've been a little lazy on writing the chemical equation for dolomite. It's actually a mixture, it's a magnesium-rich limestone, let's say. So it's a mixture of calcium carbonate, which is limestone, and the magnesium carbonate. Well, let's move to the next slide. And this is the chemistry. The limestone reacts with oxalic acid to form a brown to black patina. The chemical equations are written underneath the text. You have the limestone, calcium carbonate, the oxalic acid, and the calcium oxalate. Same thing for dolomite. Again, I'm using the lazy version of the equation. Magnesium carbonate, oxalic acid, reacting together to form a magnesium carbonate. Contaminants are going to also be part of the patina color. So in the next slide, where do you get the oxalic acid? You get that from biofilms. They can be bacteria, lichen, algae, fungus, some cases maybe even combinations of both. The biofilms can be either macroscopic, that is, you could see them without a microscope, or they can be microscopic. You can't see them, but they're still there. So let's talk about how these kinds of oxalic acid patinas are formed. We'll start with the next slide here. This is a base limestone shown in kind of a salmon color. It's going to have a dust layer. You can't avoid it. That at some point you're going to form this water film. The dust layer is going to help to trap and retain that water layer. It can be rain, dew, or when the humidity is above 50%. Water from the atmosphere, oxygen, nitrogen, whatever gases are out there are going to dissolve into this water film, and atmospheric contaminants also. So next slide, we show stage 2 of this process. When that water film gets enough goodies in it, enough nutrients, the biofilm is going to form. The spores are already there. They're just waiting for something to eat. And so Now the water, it's not really water anymore because you formed a biofilm, and now this biofilm is excreting organic acids into the water. So what you've got now, and I've made the water a slight pink color or lavender, I guess. Now you have a soup sitting on top of the limestone with a biofilm on top of it, absorbing nutrients and excreting organic acid. And it's quite a soup. It's, the organic acids, be vinegar, citric acid, and so on. But oxalic acid is one of those. And what happens is the soup now becomes acidic. We're talking a pH of 4, which is about the pH of your normal carbonated beverage. So it's acidic. But what happens is now the limestone starts to dissolve. And on the right side, you can see the calcium +2 ions are going into the soup. In stage 3, on the next slide, we are now, the biofilm and the water kind of converge together to form a gelatinous slime. And as that happens, as it starts to mature, it starts to become alkaline. It starts to go from the pH of 4, it starts heading towards 8 or so. When that happens, now the calcium oxalate, which is a combination of the calcium ions and the oxalate ions, it's no longer soluble in that slime. And so what happens is it literally snows, shall we say, on top of the limestone base and starts to form your patina. And in this last slide here is the final stage, the next slide. And here you see an example of a patina on a marble. This is a very rare photograph. The researcher or the conservationist who got a hold of this got a piece of the statue, probably a broken fragment, and made this very thin cross section. But you can see the patina, the calcium oxalate patina around there. The other thing that's interesting is you notice there's a horizontal, 2 horizontal dashed lines. One is the now surface of the marble, but on top of that is your, that's where your original marble surface was. Remember, we're dissolving the stone. It's part of the raw materials for the patina. So we've actually dissolved that much of the marble to form the patina. So if I could have the next slide, please. We're going to move on to desert varnish patinas. Now we're talking about an annual rainfall that's 4 to 12 inches. This is an example of a stone we picked up with desert varnish. It was outside of Boulder, Utah. This has 2 kinds of colors on it. It has the hematite-rich silica with the arrow shown on the left, and it has the black manganese dioxide-rich silica on the right. Let's talk about, on the next slide, the different models. There are 2 conflicting, oh, I'm sorry, I'm getting ahead of myself. One of the most common uses of desert varnish is petroglyphs. You find them all around the world. This is a boulder that broke loose from the hill and rolled down. It's in the Petroglyph National Monument outside of Albuquerque, New Mexico, literally outside. The housing goes right up to the monument. And if you look towards the left, you'll see the petroglyph, which is this circle, which could be, I don't know how to interpret it, but it looks like a person with 2 eyes. If you look to the left of it, you'll see a lighter color here. And basically, when this boulder was rolling down the hill, the patina chipped off. Fortunately, the petroglyph didn't. But if you look down towards the base of the boulder, you're seeing white stone. If you look to the smaller photograph on the right, this is a smaller rock that rolled down the hill. You can see the black patina, and then you see the white base stone there. And if you then move over and look at the petroglyph, you notice that it's a darker color. So what's happening is this boulder rolled down the hill and with the petroglyph on it, came to rest, and now the petroglyph's filling in with the patina. So thousands of years from now, it'll be pretty faint on this one. So let's move to the next slide where we talk about, there's two competing varnish patina formation models. One's a biogeochemical model and the other is a physiochemical model. In the biochemical model, it's envisioned in the mixotrophic organisms oxidize manganese oxide to manganese dioxide. And that manganese dioxide not only acts as color, but it cements the first varnish layer to the base stone and subsequent layers to each other. The physiochemical model says the black and red colors are not due to the oxidation of mixotrophic microorganisms, are due to hematite and manganese dioxide, and silica is a cement. In the next slide, we see that while these are competing models, they do have some things in common. First, they both say they're multiple layer coatings. They're deposited during multiple annual wet dry cycles, and they're composed mostly of silica. But this is the third one shows you the difference between oxalic patina and the desert varnish patina is that the layers are made from the dust that's deposited by the wind and whatever the wind kicks up from the desert floor, not the base stone. Again, the colors are due to hematite, manganese dioxide, and a mixture of both. So in the next slide, we're gonna, again, put together a model, a visual model. Stage one, we start out the same way we did with the carbonate stones. But in this case, we have the desert dust on the surface. At some point, rain, dew, humidity is going to form the water layer. And in the next model, next slide is stages 2 through finish. I don't go into the details because it's still controversial as to how the actual formation is going on. And we could spend all day talking about the two different ways, but what I've tried to show here is the different layers forming after different years, using the black to designate a manganese dioxide rich silica, the yellow to be silica, and the red to be your hematite rich silica. And in the next slide, we have an actual cross section of two desert patinas. The one on the left is from Searles Lake, California. It's on the order, it's been estimated it's on the order of 16,800 years old. The one on the right is from Panamint Lake, California. Its age is estimated to be on the order of 18,400 years old. If we could zoom in on the one on the right, there we go. Kind of looks like the Grand Canyon, doesn't it? You can see the layers. The other thing that's interesting though, and it was mentioned earlier, someone was saying that they were trying to use these to date stones. Part of the problem they're having is that you have a process of deposition and erosion going on. It's kind of hard to date, to use these to date. Hypothetically, this one here that we're looking at could have 18,400 layers. Now, I don't think it does have that much because you do have erosion going on at the same time, but that says that some of these layers are so thin you can't see it in a microscope. If I could go back to the original magnification, thank you. These two patinas are on the order of about 5 or so human hairs thick. So you could see them on the side, but they're very, very thin. So let's take a look at our definition at the bottom here. Is this a patina? Well, it's a stable, thin coating It's on the stone surface, and the appearance is changing with age. So yes, this is certainly fits our working definition of patina. And I don't know if I mentioned it or not, but our working definition is a work in progress. So we're probably going to want to modify it as time goes on. But if you look down from the top down on these, the one on the left would probably look black because the base material is pretty dark. And the one on the right would probably look red. So if I could move on to the next slide, we'll move on to just some features of desert varnish patinas. They do encapsulate microorganisms. Seen a lot of photomicrographs of that. Hence, they provide a record, both biological, geological, and climate. And the thing that just fascinates me is that desert varnish patina is a solar system phenomenon. They've been found on Mars, not just globally on Earth. If I could have the next slide, they also feel that it's speculated that there are also rock varnish patinas formed in wetter climates. There certainly are rinds formed. We're not going to be covering those today. However, at this time, there's little or no research available on rock varnish patinas. There is some mention of it, and I'm working towards getting as much information as I can. Rock varnish patina chemistry, it's probably different from the area where the annual rainfall is less than 12 inches. And the morphology is probably different. It might be, they're probably single layers because you have more rainfall to generate. So let's move on to the next slide on artisanal. Oops, sorry.
Let me interrupt for just a second. Could
Sure.
I ask you to please mute your microphone so we don't interrupt the speaker? Thank you.
This is an example of a rind or a rock varnish patina. I suspect it's probably a rind. We're looking at the Moai statue on Easter Island. They're made from yellow gray tuff. Tuff is just whatever airborne things come out of a volcano, and they get metamorphosized into a stone. You probably have a gray rind at the top above the surface, and you have a yellow rind under the underground. This particular research group was privileged enough to be able to excavate this particular statue to get permission to do that. Is this a patina? Well, it's certainly stable. Remember I said a definition is a work in progress. If it's a rind, it's not necessarily thin the way we've been talking about it. So we might have to kind of modify our definition as we go along in these kinds of discussions. It certainly is a coating, and it certainly has changed its appearance with time. So it probably fits into the patina realm. It's just we've kind of constrained ourselves by saying thin. If I can have the next slide, then we'll move on to artisanal patinas. This is an old and ancient practices. Agate has been dyed black. It's around at least the 1st century, if not sooner or older, because Pliny mentions it in his Naturalis Historia. They were dyeing the agate black because they wanted it to look like black onyx. Jade has been modified. The color has been modified since the 13th century in China. And bronzatura marble statues were very popular in 18th century Italy. My daughter Stephanie told me that when she was in studying in Italy, that one of the docents told her that the bronzatura was very popular with Nero. So if that's true, it's possible that bronzatura is even older than the 1700s. Artisanal patinas are often formed with 2 or more combinations of heat, mineral acids, organics to give the black color, or pigments. For example, the if you look at the agate, they will soak it in honey at a high temperature for a number of time, and then they will put it in very hot or very warm sulfuric acid. That's something I wouldn't even do in my lab, but the ancients were doing it, so, and it's being successful. You can also put oils and waxes as a final stage on these. So let's talk about different types of artisanal patinas. If we can move on to the next slide. Now these are the materials that are used. The coatings, which would be adsorbed. So this would be the first stage of the patina definition. Wax, varnish, and oxalic acid. Stone conservators are looking at taking a freshly cleaned stone statue and putting the dark patina back on the statue. And as you can imagine, there's some pretty lively debates about whether or not they should do that. But the point is from all the research that's been done, they're actually starting to use the whole oxalic acid patina concept and the science of it to start putting it back on freshly cleaned statues. Stains, which absorb into the stone, inks, pigments, which are metal ion solution, teas, soil, oils, and dye, water, the practice of yoseki, and wet stones. So let's talk about some examples of artisanal patinas, shown the first one in the next slide. The one on the left was made by a master stone carver in China. This is a stone without the patina applied to it. My first guess would be this is a dolomite based on the color. However, you can't tell from a photograph. But if you look to the right, now the stone, and this is a different stone, but the same material, the stone has that old, venerable, aged look that Tom mentioned at the beginning of the seminar. Let's move on to, I believe tea stained is next. Yes. Tea absorbs into the base stone, its cracks and pores. The stone minerals and tannins from the tea form what's called chelate complexes. Tannin molecules are very big. They surround and cage the mineral metals. And this chelated mineral complex now is a color that's often darker than the natural color. Higher temperature helps things, it accelerates the staining. Tea stains are typically stable, and in the next slide, they have an example of one that I did. You have the Wisconsin limestone here, and then to the right of it is another piece of the Wisconsin limestone. Now you can see the stained color. This was done over a period of 5 days with some black tea that was at a concentration you'd never be able to drink, with a little bit of detergent and a lot of heat. And this thing has retained its color. The one on the right has retained its color for at least 90 days now. Let's go back to our definition. Is this a patina? Well, it's stable, it's thin, but it's not a coating. It's absorbed into the viewing stone. So it's not on the surface. Its color has not changed with age. So yes, it's really cool, but it doesn't fit our definition. Again, working definition, so time will maybe start to include this. In the next slide, we are going to talk about yoseki. This is where stones are placed outside in the sun on shelves, periodically wet from rain, snow, and humidity. We also found out last night from a gentleman who's an expert in this from Japan that these are also tea stained. And a really interesting point was they're even covered with rice flour as part of the yoseki process. So it's a very complicated process. It takes many years to obtain the desired patina. We've not found any scientific papers. However, we've been promised an article on this, but we can extrapolate some things based on what we know about patina science, and that if it's a carbonate viewing stone, it's probably an oxalate patina because it's being kept wet. And of course, if you're putting the rice flour on it, you're providing nutrients for the biological films. There might be possibly leaching of the silicate materials from silicate stones, or chemical weathering, which would be your rind forming. And you might even be leaching oils from the wood into the stones as part of the process. Again, we don't have scientific papers, so we're not sure. We're just doing conjecture on what may be going on. If I could have the next slide, please. We're going to talk about, can water be a patina? Here we have an example of a granite river stone. The tip of it to the right, you'll see, is kind of a pink color. That would be probably a feldspar. And then if you look to the right, now the stone is submerged in water, and you can see that the feldspar part of it is more reddish than the dry stone. If we can go, yes, thank you. Go down to this diagram. What happens with the dry stone is the surface is rough, and the light basically comes down, strikes the surface, and reflects off of it. But when you start to talk about a wet stone now, if we can go to that diagram, things become way more complicated. In this case now, the water covering the stone smooths the surface. Now, as far as the stone looks like, it's atomically smooth. The light comes in, strikes the water, and enters it. As it enters it, it bends. That's called refraction. In the process of moving through the water, it also diffracts. It starts to separate into or shift towards the red portion of the white spectrum. And then it'll reflect from the surface underneath the water. And as it starts to exit from the water, it refracts again, it bends again. So it becomes a much more complicated process. And basically what happens is your whetstone is more colorful and more intense color because of physics, not necessarily because you've altered the surface. So on the next slide, we basically review our definition again. Is water in a wet viewing stone a patina? Well, it's not stable because it's going to dry out. It is a thin coating. It's on the surface, but the color is not really changing with age. We can move to the next kind of artisanal patina. What about polishing? Well, if we compare oxalate patina with a polished stone, and the stone on the right is a polished sphere. It's a polychrome jasper in part of my collection, or part of our collection. Yes, you're removing the original stone surface with both. However, with the oxalate, you're replacing that original surface with the metal oxalate. When you polish the stone, when you're done, all you've done is smooth it. You have the same chemistry, same crystallography, so you really haven't changed the surface. So basically, you don't have a coating, you haven't changed the surface, so polishing's not really forming a patina. And then finally, I think the last two slides, we've got the takeaways or the summary of this. Patina research encompasses a wide variety of art, engineering, and scientific disciplines. And Sue's going to give you just a quick list at some point during the discussion. Different types of stones develop different types of patinas in different environments. Patina chemistry and formation mechanism are different for the different types of patinas. Patinas can be either a single layer or multiple layers of different materials, depending upon the type of stone and its environment. Remember, the desert varnish patina looks like a miniature Grand Canyon. And then finally, the last three takeaways in the next slide. Patinas develop over long periods of time, but they can also be eroded from the stone surface. Patinas have been part of the artisanal stonework around the globe for millennia. And research on stone patinas is ongoing, and the discoveries that are made will shift our paradigms and thus improve our understanding of patinas. If you haven't done so already, I would recommend reading the November 20th VSANA feature article written by Doug Wickley and Tom Elias. It provides a really good overview of patinas. So with that, I'm going to turn the control of the show back to Tom.
Okay. Well, thank you, Steve and Sue. The dynamic dual in geology relates to patinas. Thank you very much for spending the time and effort to pull all of this information together for us and to inform us about what is known and not known. I have put their website here and their email address if you want to contact them in the future about specific questions. But now I want to thank all of you for watching the program. I'm going to open this up for questions, and I'm sure there's going to be